So, let's get right into it. When you think about computer code, what comes to mind? Probably lines of text, right? Maybe a stream of ones and zeros. But what if I told you that inside all that complex software, there's a hidden shape, a secret geometry that we can actually map out, explore, and even use to navigate its most dangerous parts? Today, we're going to uncover that secret landscape. This one phrase, it just nails the problem. See, modern software isn't some simple straight road. Nope. It's more like a massive city with millions of things all happening at the exact same time. These are the concurrent interactions. And trust me, without a map, it is pure chaos. And that's the big question, isn't it? If your program is like a city with a million cars all moving at once, how in the world do you draw a map that can predict traffic jams, spot the dead ends, and guarantee a safe route from A to B? Well, that's the challenge we're going to tackle. Okay, so before we can even think about drawing our map, we have to really understand the territory. Let's get a super clear picture of this concurrent chaos and what it actually means. Just think about your own computer for a second. Right now, you've probably got a web browser open, maybe some music playing, notifications are popping up, all at the same time. And each of those things is itself doing thousands of operations. Now, when all those operations start to overlap and fight for resources, it becomes incredibly hard to predict what's going to happen. It's that complexity that leads to bugs that are just notoriously impossible to find and fix. So, how do we bring some order to this beautiful mess? Well, the answer comes from a totally unexpected place. Geometry. Yeah, we're going to trade in our debugger for a compass and a map. And that is the perfect way to describe it. It's surprising because, let's be honest, we don't usually connect code with shapes. And it's beautiful because it gives us this elegant, almost intuitive way to see and understand what's really happening inside these insanely complex systems. This is where the idea starts to get really visual. Think of it like this. Every single possible sequence of things a program can do is literally drawn as a path on some kind of geometric surface. A really simple program might just be a single straight line, but a complex one, whoa, it could look like a huge sprawling network of trails going everywhere. But here's the really crucial insight. Not all of these paths are truly different. Imagine you've got two different routes on our map, but they start and end at the same points. If you can kind of smoothly stretch one path into the other, like it's a rubber band, without breaking it, they're considered equivalent. In the world of programming, this means two totally different sequences of operations can end up with the exact same result. This idea, it's called homotopy, and it lets us simplify our map in a huge way by just grouping all those equivalent journeys together. But this isn't just any old map. To actually be accurate, our map of code has to follow one very, very important rule. A rule that makes it completely different from any map you've ever used before. Exactly. You can't just turn around and retrace your steps. On this map, every single road is a one-way street. Why? Because in the world of computing, you can't turn back time. I mean, think about it. Once a calculation is done, it's done. Once a piece of data is sent, it's gone. This fundamental law, the forward arrow of time, has to be built right into the geometry of our map. A normal map it won't work. And this creates a huge difference. On a normal map, if you can walk from point A to point B, you can always walk back from B to A. But in this special directed space for code, all the paths only flow one way, forward. It's like the map has a built-in current that you just can't swim against. And of course, scientists have a name for these special one-way journeys. They're called directed paths, or D-paths for short. These are the only valid routes on our geometric map of software. And thinking in terms of these D-paths is the absolute key to accurately modeling how a program actually behaves. So, we've gone to all this trouble to create this special geometric map with one-way streets that represents our code. So what? What's the payoff? Well, the payoff is that this map makes all the dangers startlingly visible. It shows us the hidden traps. It shows us the places where our program can get totally stuck, where it can break down or just spin its wheels forever. It basically reveals the digital dead ends before our users ever have a chance to run into them.
With this map, all the potential problems become super obvious. Like an unreachable point is like an island with no bridge. It's a part of your code that can never, ever be accessed. An unsafe point is like a path that you know leads straight off a cliff. It's a known bad state. A doomed path is a trail that just kind of fizzles out in the middle of nowhere, never reaching its destination. And then there's the most famous hazard of them all, the deadlock.
A deadlock is the ultimate digital traffic jam. It's when two different parts of your program are each waiting for the other one to do something, so neither of them does anything. They're just stuck, frozen in time, and the only possible move is to stand completely still. On our map, this is a literal dead end, a place you can get to, but you can never, ever leave. So what we're talking about here isn't just some clever metaphor. No, this is a revolutionary new tool. We are literally building a completely new kind of atlas for the world of software. By using this directed geometric semantics, computer scientists can do way more than just test code. They can formally prove that it's safe. They can use the full power of mathematics to guarantee that a program will never hit a deadlock, that every single path will safely reach the finish line. It's all about building software that is fundamentally more reliable. This new atlas, it basically gives us superpowers. It simplifies crazy complex problems by showing us which actions actually matter. It even lets us use these advanced mathematical tools to, get this, count the number of holes or voids in our map, revealing the fundamental structure of all the program's possible behaviors. This is truly the foundation for a new way of thinking about concurrent code. And that's really the ultimate goal here. We're not just fixing bugs, we're developing a completely new language, a new understanding of how to build these complex parallel systems. We're moving from chaotic guesswork to geometric certainty. And that's the thought I really want to leave you with. We've just found this hidden geometric world living inside our computers. And it just makes you wonder, what other complex systems, from neural networks to financial markets, have secret shapes that we just haven't figured out how to see yet? What other incredible landscapes are out there just waiting for a mapmaker?